没有问题。
make things ridiculously easier. I definitely need to make sure.
我跟你讲，上次脸上还是气泡水。那叫你今天出门好好再买。
All right, well, my bad. I'll get that up next time. There are about 3 or 4 videos by a woman who does an excellent job explaining Smith charts. I'm going to do it today. I'm sorry, I thought that been posted, but for some reason. Anyway. So we're talking about the Smith chart today, and I did put something up at that. We will cover the Smith chart, correct? Mm-hmm. All right, did you read anything about it? How many read something about the Smith chart? All right. I could go through the formal proof of how it was developed, but I think if I have time, I'll come back and do that. What I want to show you is its usefulness. So a Smith chart, if you turn in your book and look at, I sent you them. I hope you brought some to straight edge. We're going to go through this. So, in the book, I forgot the exact place it starts, but I'll give you that. Because this tool is primarily used for impedance matching, so you can get rid of any reflection. So it starts on page 64. You can read through the beginning of that. Or it's shown on page 63, and I sent you something. I'm going to show you the usefulness of it, because that's really what you want to know. But I can go through the proof with you. I prefer you read it first. The proof's a little long. It's a little boring, too. But here's how this thing works. This is a Smith chart. I hope you can all see that. Let's get a better marker. And what happens is it's going to have like an equator there. All right. Then there's going to be a circle. This is the critical one. It will be this way. It's symmetric about the equator. I call it the equator. And this has a value of r equal 1 that goes right through the dead center. Can you all see that? It'll show something that's just got like a 1 next to this, right here, this circle. You all see that, class? All right, there's 2 other points they're going to make. There's going to be a J here at the North Pole and a minus J here at the South Pole. That's a 1, that's a minus J1, and it looks like this. And what this is something that actually is graphically going to show the reflection coefficient. Now, I know I'm saying a lot of stuff here that doesn't make a lot of sense yet, but I'm going to show you how this works. All these lines that intersect the circle normally, this is going to be minus J 0. Plus J 0.8. There'll be a minus J 0.8. All the ones that intersect normally on that outer circle have an imaginary value. All the ones that'll be an R equal 2 here. Can you all just take a look at your Smith charts and see that? You all see how there's concentric circles that are growing larger and larger, all of them hitting here. The one that goes right through the center there has R equal 1. And then there are also trajectories of circles where the center point is outside of this circle, and they intersect here. You all see this? Can you at least appreciate this? All right, now, here's how this Smith chart's being used. When you start and you want to do something with this, you start and you have a load value ZL, and that can be anything, doesn't matter what it is. It can be just strict real, it can be imaginary, it can be real and imaginary. You're going to have a characteristic impedance of the transmission line, Z0. Y'all follow me on this? Okay, now at that point, the way you begin is enter the Smith chart with a single dot that is going to be a location of something called the normalized impedance. So the first thing you do is get ZL, and that's going to be capital ZL over Z0. So it's called normalization. You divide the characteristic impedance into the load to get a value. Everybody with me on that? After you get that value, you plot it. It can be anywhere, doesn't matter. So it might be here, and if it was here, if this was ZL, label that as 0.1. What that does you is give you the magnitude and the angle of the reflection coefficient. Now this doesn't mean a lot to you, and it's not really that important right now because you're saying to yourself, well, if I want the reflection coefficient at the load, this would be at the load, you can simply take ZL minus Z0 over ZL plus Z0. You all agree with that? That would be the reflection coefficient. And if you divide the top and bottom by ZL, or by Z0, you would get ZL minus 1 over ZL plus 1. Y'all follow me? Now that has a real and imaginary value. We don't know what it is, but it does. That real and imaginary value there is what this represents. The length of this line from here to here is going to be the reflection coefficient's magnitude. And the angle that is measured from here to here will be the angle. That'll be the angle. Now, it doesn't mean much to you just saying that's the actual value of the reflection coefficient magnitude, but at the bottom of the Smith chart down here, if you take a look, I may put this up on the overhead if you have more questions. How many have access to a Smith chart right now, Friday? Do you have one, sir, or not? Anybody have an extra, do you have your book here now? Anybody have an extra Smith chart you can give that to me? All right, hand it back. Anybody else not have a Smith chart? Just tell me. You don't, somebody hand him an extra one, please? You all have, you can open your book, use your book if you got it. It doesn't matter. I just want to make sure everybody has access to a Smith chart. You got one? Okay. And you got it, right? All right. Now look at the bottom of the Smith chart down here. You're going to see some, depending on the type you have, one of the things they're going to have down here be a line like this, and it'll say reflection coefficient. See if you can locate that. All right. Now, the reflection coefficient right at the center is 0. As it grows, it gets larger and larger. Usually it's measured from the center here. Just take a look at that and put down, measure this distance with your compass. This is the way you do it. Take it down here, and now you see the magnitude of the reflection coefficient. You all see that, class? You all see that at the bottom of your Smith chart or not? Do you? Look at the very bottom. See that they have these straight rows down there?
There's reflection coefficient P and reflection coefficient E or I.
Oh yeah, I see
Yeah,
that.
and if you, hold up. Let me just do this. 'Cause I'll save myself some trouble. I'm gonna shut that off and put down the screen. But I'm gonna get back up here because I found that it works much better when I'm out here doing it. Give me 1 second, I'll show you stuff.
That looks so much better.
Yeah, the glare is brutal.
Yeah. Nice. This guy's a professional.
So, this is what you're seeing in your book, right? All right, if you look down here, look at the bottom here, you're going to see right here, reflection coefficient. You see this right here? Now, it may be a little different. These things, this may appear at the top on some of them. If you take a look at it, measured from the center, right here, to any point along the line, you see how the reflection coefficient's magnitude gets larger and larger, and if it goes right to the end here, it's 1. That means it's proportional to the length from here to here. This would be a length of 1, and wherever it goes up to there is going to be the proportional length. Now, do y'all see that, class?
You don't see the screen?
Oh.
I couldn't see where
Sorry,
you were
sorry.
pointing.
I'm going from, but I should say, if you go from the center right here to any point is going to be the magnitude, if whatever point you put in is ZL. If you go right to the rim out here, the reflection coefficient is going to have a value of 1. It means everything's reflected. Now, if you look there, you would be right on the rim would be a J value with the real value equals 0. And I'm going to go through this, and I know you have a lot of questions. As I'm talking, I realize how many gaps there are in what I'm saying. But when you see problems done with this, it'll make sense. Now, if you also look here at the bottom, right here, at the bottom here, there's going to be something that says standing wave ratio, right? You all see that? If you take that same measurement that you had with your compass and just put it there, you can get the standing wave ratio. Some of you are thinking, but I can get the standing wave ratio by simply taking 1 plus the magnitude of gamma over 1 minus the magnitude. That's absolutely true. It's provided there also, graphically. Do y'all follow me? As a matter of fact, you can get the magnitude of reflection coefficient and that angle just by doing the equation I put up a second ago. Do y'all follow me in that class? So, it's not necessary now, but here's what's going to be happening, and I'm going to take you through this. I'll get up there and do this. Up here, it'll be a lot easier. Okay. So anyway, that's how you get the magnitude and angle. The angle is on, if you look at the outside, or actually, in mine it's on the inside rim, you'll see angles in degrees, and they'll start at 0, and then go up to about 90. But we'll talk more about these things. Right now, just appreciate how you get into the Smith chart. Now, next thing I'm going to say, what I'm showing you basically is on page 70 in your text that you have, about how to get magnitude and angle by using a Smith chart. Can you all see that there? It's always showing you. Then it doesn't that much. So now some of the usefulness of the Smith chart. Suppose I want to know what the value is of the input impedance right here, Zn. I want to know just by using a Smith chart. I'm going to show you how to do it with a Smith chart. This is really valuable back in the day before calculators were readily available and everybody had to use slide rules a long time ago. So if I take ZL and point it in here, I get a point. Now, what you normally do, just locate as point 1, take a straight edge, and you draw a line right out there. Can you all follow me on what I'm talking about? We'll do an exact example with numbers, but I'm just showing you. Then you're going to see something on the outer rim here that says WGG. That's wavelengths towards generator. Can you locate that? The outer rim. How many can locate that and see that? Can you see it over here? What? Wavelengths towards generator. Now, as you move, if this is the load, you can only move towards the generator, right? So if you figure out how many wavelengths you move, we can get the input impedance from this. If you look at this, and it's going to have in your Smith chart, on the wavelengths towards generator, you're going to see markings, and I got to explain this. I call them mile markers. It's like on a highway, they're mile markers. So you're going to see a value out here. And it's going to be something wavelengths towards generator at the starting point. I'll just call that P1 for where you started. It'll be wavelengths towards generator. Now, if you say this thing, I'm going to move, say, 0.5 0.1 lambda, and I want to know the input impedance here. Y'all hear me on this one? If I want to move 0.1 lambda, then what I'm going to do is take this, whatever P1 is, and I'm going to add 0.1 to it. I'm going to move along this arc, and I'm going to find that point. So this would be like 0.1 plus 0.1 lambda, wavelengths towards generator, and that's the point. Then I'm going to take this, I'm going to draw a line right from the center to this point, straight through here. And then, y'all follow me what I've done? I've just gone a certain distance, wavelengths towards generator, and I just put a line on it. Then you take your compass and put the point of it right here, and then you draw an arc of constant radius here, like so. This is where we started, right here. This is the second point. That point 2 right there will have a real and imaginary part. You all follow me on this? When you take that real and imaginary part and multiply it by Z0, then you get the impedance, the input impedance of the line right here. You all with me? I want to do an example so you see it. Now, how many have a Smith chart they can work with? And a compass and a straight edge. All right, if you don't have a compass or straight edge, try to borrow your neighbors. But I'd like everybody to try this with me. I'm going to go through a real example with a fresh Smith chart. You're going to help me. And I'll be the one, where's the book? All right, let's do drill 2.2 on page 73. With me? It's drill exercise 2.2 on page 73. I'll take you through every part of this, make sure you understand it. And so if you have a fresh Smith chart, you're way ahead of the game. Use your straight edge and stuff like that. Do what I'm doing. So first, for this one, I'm going to erase this and get a fresh Smith chart of sorts. I know there's so many gaps in what I'm saying, but it'll be taken care of as we do the problem. So first thing is, what is ZL given as? For that, anybody?
You said drill 2.12?
Yeah, it's on
100 minus J 100.
All right, so they give you 100 minus J 100. And what is Z naught?
50.
All right, so when we get ZL, we take capital ZL over Z naught. And that's going to be 2 minus J2. Can everybody see that? You all agree with that? I'm going to recreate this Smith chart. I'm going to show you where it is, and you're going to find it too. This is actually maybe not the best example because it's a fairly close into the edge. But this is the R equal 1 circle, and here's J1. Here's J minus 1 here. All right, now these are just trajectories I'm showing you. Don't worry about that. Now, for a larger value of the real part, our real part is 2, there's going to be a circle inside that one. And it'll be R equal 2. Can you locate that? And there's going to be a value of minus J2. If you look down here, there's going to be minus J2 about here, and you're going to see this trajectory come like this. Do you all see that? Please take a moment, make sure you can see this. There's 2 minus J2. The real part, the value 2 here, should be a circle about there. Can you locate that? How many can see the R equal 2 circle? In the back? Can you guys see it? Anybody not see that?
Do you see
If
the
you can't,
J2?
raise your hand.
Yeah.
I'll make sure you can.
No.
Y'all with me, guys? Now, there's trajectories down here. You'll see
Two is this
minus 1 here. I mean, it's going to just say 1, or minus 1. This is going to be minus 2. It's where the line normally comes into the edge of that circle. Take that and trace it back. In the intersection of those 2 lines, this is minus J2. This is your point 1. So label that point 1.
Just
Okay?
to add the J.
Y'all got that? It's not hard to do. We're going to do several problems, but I want to make sure you're doing them, not just listening. How many have straight edges and compasses here?
Wait, can you go back a couple steps? I just found the J1 and J2.
All right, this is minus J1.
Oh,
This
yeah.
is minus J2. You found that?
Mm-hmm.
Did you find R equal to the inner circle? You can?
Yes, sir.
All
Yeah.
right, where they intersect is your point, P1. That's the point, this is the entry point. This is ZL, and it's the first point. It's where you enter. I'll just call it, I'll label it as 1 right here. Y'all with me? Now, if you have a compass, take it and go put the point in the dead center of that. Take that right here,
Oh, yeah, I got
and
it.
then put an arc like this. It's going to be a circle of constant value gamma. All right? Y'all follow me? Just make a circle there. The order of these steps doesn't matter. Yes?
Oh,
Did you have a I mean, you know what I'm talking about. Just, you're going to have a compass. Constant radius. You put the center, right in the center of the circle. You take the other end and put it on that ZL, that point ZL. Now that technically is the magnitude of the reflection coefficient when you measure it down at the base. And we'll talk about that in a second. Then when you draw the circle, that's constant reflection coefficient around it. So this is not drawn real well, but what I'm really trying to show you is this right here is going to be the magnitude gamma. It's a constant value of gamma. Do y'all follow me? All right, now, next, here, take your straight edge and shoot a line right out here. And you're going to get a number that says wavelengths towards generator on the outer edge. So can somebody give me that number? It'll be like 0.27, 0.28, something like that. Take a look. It'll be on the outer part.
0.29, I think.
How many see 0.29?
29.1.
0.291. You got it? Over here, you guys see that or not? All right. Who sees it back there? Can you show him, please? Just get up and show him. I'm going to make sure everybody sees this. Do you see it, sir? Pardon me?
Are those ticks and twos?
The 0.2291 on the outer edge, 0.291, 0.295.
Yeah, they were on
You see it?
I don't know if specifically
Over here?
to be in this.
I'm hoping we're right
Make
at
sure y'all
2
do it.
decimals.
Do you see it or not, sir? You got it? Back there?
You got it.
You guys, anybody not see it? Do you see it, sir? Or not? Okay. Hold on. Nick, do you see it or not?
Yeah,
Can you show me? Get over there and show me. You see it? Over here, you guys got it? All right. Now that's the starting point. Think of it as a mile marker on a highway. If you come in, exit 57, mile marker 57, all right? Now we're going to move. How far are we going to move? We're going to move towards the generator. We're at the load. You can't go towards the load. We're going to move in a direction towards the generator. And how far does he say? Well, first of all, what we'll do what he says sequentially. Now, what's the second part of that? We've located the points. Now what?
We go
This
down.
is point 0.291 lambda. They won't show lambda, but it means lambda. Go ahead, Rick.
Hey, you're talking about part A of that?
Yeah, what else does he ask for?
Reflection coefficient, VSWR.
All right. How do you get the reflection coefficient? If you got do you have compasses there? Everybody?
Yeah.
How many do? How many have some way of measuring it? If you have a straight edge, just kind of estimate that. Take that and go down to the bottom of the thing that I showed you. Then it'll have like reflection coefficient, I think it's COEF. And here is 0, out here is 1, and just start at 0 and measure the length of that. Somebody tell me what that is if you don't mind.
The length from the origin to the intersections of the J and the real number. Okay.
I mean, it'll be, you take this distance right here and put it right here and tell me what you read.
0.61.
0.61? How many got about that?
I got 0.
I'll give you a second.
I got 0.38.
He's saying it's 0.61. This is on the bottom. Now, we can figure it out without that, right? You can just say, if I want the reflection coefficient,
I
right?
got like
I
0.3.
can take
Yes.
this 2 minus J2
Yeah, from
minus
the origin
1
to the
over
point where it
2 minus
intersects, right?
J2 plus 1. Or this is going to be what?
And you got
3 minus
0.6?
J2 over, I'm sorry, 1 minus J2. 1 minus J2 over 3 minus J2. And that'll
Look at
be,
the reflection
can
coefficient
somebody
on the
just
line.
do this on your
It's
calculator?
different.
1 minus J2 over 3 minus J2 and tell me what it is. Magnitude and angle. Because we're going to see that that's exactly
You
the
get
same.
0.62.
What did you get? Did you get 0.61 at some angle?
Okay.
Anybody?
We need to, okay, gotcha.
Wait, what are we look? What are you asking?
Top one is jacking me up.
But I want it first, I want this, because this is mathematically exact. But I'm going to show you how the Smith chart gives us that. What'd you get?
I got 0.62, which is what I measured as well.
0.62. What angle? In degrees? We're going to go on the Smith chart and see the angle to us.
to do
It's
that.
the angle.
How do you do the angle?
It'll be a negative angle, I think.
Negative 30? Is it on the
Pardon?
circle?
No, I'm asking just for this. We're gonna get to that in a second, but you're right, you're right. You're ahead of me. Go.
I don't know how to get the angle from the distance.
Well, I'll show you in a second,
Mhm.
but first, I wanna make sure, what is the angle on that one? The magnitude's 0.62, go ahead.
You said reflect coefficient of P or is it E or I?
It should be reflection coefficient.
Use the E or I one.
It'll be, E, this is an old way of doing it. E is a symbol for voltage. Back in the day, and in England, they still use it. They just use, I don't know exactly the reason. So it's a voltage reflection coefficient. Voltage is the same thing as ours. Same thing as the standing wave ratio. Go ahead.
The angle is negative 29.74.
All right. Minus 29.7, did you say degrees?
Yes.
All right. Now, if you look at your Smith chart, just listen to me now. This is the magnitude from here to here, reflection coefficient. Then if you go to the edge out here, you're going to see angular degrees. Can you see that? This is going to be 0. And if you go this way, it's positive. If you go this way, it's negative. This is going to be, they may just have it as an extent, but it'll be either minus 29 degrees, or you're going to see something that'll have like 29, but it's measured from this point. Do you all see that in the outer part? How many do?
Yeah.
It'll be about 29. You're going to always get a little
30.
slop.
Perfect.
Now, do you guys see that? Back here, do you see it? Okay. Does anybody not see it? You see it? Anybody not see it? Sir, do you see it okay? Or? Okay. Everybody? I got to make sure. Once you get used to this thing, it's easy to use, but you have to get used to it. All right. Now, that doesn't mean a lot right now, but now we're going to move, right? Now, the second part of this is what does it say? This is,
Find the VSWR.
well, okay, we can do that by just looking at different, this is drill 2.12. All right, guys, you know how to get the VSWR? We could do it without this, right? On the same area where you measured this, look up to the top part. The very top one will say either SWR or VSWR, depending on your Smith chart. Do you all see that?
That's
Now,
the standing
just
wave.
measure it from the center out.
You get 4.
And the further out you go, the larger number. Right dead center is 1, and the VSWR on this one is what, 3 or something?
4.
Is it 4? 4 1/4? Is that what it is? So VSWR, which is measured at the top part here, or SWR, or ERI, or whatever they have it, is about 4.1? 4.3 approximately? Okay, now, you at least are getting familiar with what information's available just with a glance, right? No calculators involved, just a couple of sharp pencils and straight edges and a compass. But now we're going to move. Now, remember when we calculated Zn back here, and use that equation, that was equal to Z naught times quantity ZL plus J Z naught tangent of beta L over ZL plus J, or over Z naught plus J ZL tangent of beta L. Remember, it was kind of a pain, right? We're going to do that same, and remember, this was invented before really calculators. You had slide rules, but this is a trivial way of doing it. So now, I started here, right? Now I'm going to add the value of the length. The length of the line here is what? 0.3, I think?
0.334.
All right. Lambda. Now this is very important to pay attention to this. So I want you to listen to me carefully. When you have a Smith chart and you come in and locate the load, the normalized load in P's, as you move wavelengths towards generator, you're moving in this direction. You all follow me? All right. As you're moving around here, here's a real important point. When I start here and I keep moving around, if I came all the way around back to here, which would be 1/2 wavelength, I'm back at ZL normalized, right? Every half wavelength you move from the load, the impedances repeat themselves. The reflection coefficient, everything like that. So if this is ZL here as the input impedance, when I'm right here, the normalized input impedance would be my small ZL. If I multiply that by Z naught, it would give me the input impedance would be ZL every half wavelength. Y'all with me? But because it repeats itself every half wavelength, if you look at the markings on here, you're going to see out here, the angle is 0 degrees. Take a look. You all see that? Wavelengths towards generator? How many see that? the leftmost part. Can you all see it? You see it? Yeah. Over here, you're going to see 0.25. That's 0.25 lambda. It says if I move from here all the way over to here, I moved exactly a quarter wavelength, right? If I keep moving around here, I move a half wavelength. Now, when you do this, and this is a really important point, we came in here and we had, this is our mile marker, 0.291, right? We need to find the value of the input impedance here when we are moving that far. So now we're going to go ahead and say, I want to see what the input impedance is when I move 0.334 lambda. Now just think about what I said. If I moved half of a wavelength, or quarter wavelength, I'd be here. Follow me? I'd be at the exact conjugate point on the other side. It's halfway around. You all with me on that? But I'm not going to move there. I have to move 0.334 from here, which means it's somewhere down here is the value. Now here's how you find that mile marker, because it's going to be different than you think. I start down here, and I say, now I want to find out where this mile marker is going to be here. I want to find it. So the way I get that is wavelengths towards generator for 0.2, the input impedance. I say that's going to be equal to, start with the wavelengths toward generator you were at, which is 0.291 lambda, then add that to it, which is 0.334 lambda. So what do you get? It's going to be greater than 0.5. Just tell me.
0.65.
Pardon me?
0.625.
0.625 lambda. You all see that? Now that's greater than 0.5, right? Anytime you go more than 0.5 lambda, subtract 0.5 lambda. If it was greater than 1, you would subtract 1 lambda. In integer values of it's really n times 0.5 lambda. So you subtract 0.5 lambda from that. Now what do you get? That's 0.125 lambda. Isn't it, class?
Yeah. Yes, sir.
All right. Now that's the point you want to locate. Because remember, every time you go around, it's a half wavelength, right? We started here. We're going to add. Here's a quarter wavelength, but we need to get to this point. If you look up there at the top, you're going to see 0.125 lambda in the outer part that says wavelengths towards generator. And this is wavelengths towards generator. How many can locate that? It's the outer rim. You all see that? Make sure you do. Do you see it in the back? Over here, guys? Anybody? Do you see it? Mason? All right. You got it? You guys back there? I want to make sure everybody, do you all see it? Everybody. If you don't, just let me know. I'll send somebody or come down myself. Now, you see you made that compass circle, right? Now, take a look at this point here. And tell me what the real value is. There'll be a circle like this coming down. It's going to be less than 1. I can't tell you what it is. And then there's going to be an imaginary value here. Everything in the north hemisphere, the J's are positive. In the south hemisphere, they're negative. So tell me what this point is in terms of maybe normalized value of real and imaginary. That would be the input. It's normalized. Zn. What is it? The real part is going to be smaller than 1. And the imaginary part is point J, something less than 1, I think.
Is it 0.4?
Take a look. Can you see it? How many got around 0.4? Is that right? Can you see it?
Beats me. Yeah, I don't get that.
Well, what you're doing is, if you located this, take your straight edge from the center, right here, and draw it out there. It's going to intersect this circle that you drew. If you take a look at this circle is going to have a real, this is the circle that comes through the hemispheres. All right, the real value, and then if you look at these trajectories, there's going to be a trajectory here that comes through. So what's the value for the real value?
It's kind of a weird.
0.45.
0.45. And then plus J, and what's this value?
Like 0.
What is it?
Yeah, 0.9.
0.9? Is that right?
Mm-hmm.
How many got approximately that? You're going to get fudge. I mean, you're not going to get exact, but you're going to get real close once you have sharp pencils. Did you guys get that back there or
What
not?
did we just get?
The
All right, who didn't get
you
it?
get 0.9 on the
Please,
imaginary.
let me know. I'm here to help. I'm not trying to, this is not supposed to be baffling. I just want to make sure everybody can see it. Usually it has to do with something
No, you
where you
go-
don't see it
it's
well
like right here.
because
Then you follow
either
that
your
up.
glasses
Point.
are
Oh,
like
yeah, that's
you
right.
see it? All right, you guys see it here?
Yep, you're absolutely right. So yes.
I bet there's such an easier one to print. I bet there's like one you can print that makes it so much easier.
Yeah, I don't know how much of like all this junk we need, like wavelengths towards load or like the angle of transmission coefficient. There's definitely a simplified one we can do. And all those little boxes aren't helping us out at all. I can't see shit.
I don't know what any of those are.
Man, my eyes hurt just looking at it. I'm seeing pancakes.
It's kind of simple though.
Yeah, it's not too bad. Just gotta practice it, I guess.
Yeah.
Like if you ask me in 5 minutes to do this again, am I gonna be able to do it? I don't know, but maybe I'll remember some of it.
I mean, I can get some numbers.
I can find the reflection coefficient. I guarantee that.
Yeah. Actually, I don't think I'll be able to do that.
Is it define the weird Z? Is that Z all over Z naught, or is that? Oh yeah.
Yeah, it is. It's like the lowercase c.
What like that? Is that a Greek Z?
It's a capital. It's a cursive c. Yeah.
Cursive Z. Goodness, why are there so many damn Z's? Pick
It
it up
looks
a
like a
letter.
Y.
Looks like a backwards 3.
Yeah.
That's a right way 3. Goodness gracious. My brain's fried.
Are we gonna have this? Because if we have this on the,
We definitely will.
I could just sew.
It's literally just like an easier way of doing
Yeah.
what we did on that course.
I might just write down how to do everything on the back.
Yeah, like that's what I did. I had like a Smith chart with like the key on it. Like you have everything written down on it.
That's what I'm
And like all like this is how you get the VSWR. This is how you get the reflection coefficient. This is how you get Z in.
I'm still printing that out. I don't think you'll care.
The only thing we have to do that's Z in, but that's like the cursive Z in. I don't know. I don't know what the difference is between the two.
I bet the video is also very helpful.
I'm sure it is.
There's like coordinates, and in geology I hate coordinates. God.
Look at a topographical map.
All right.
Exactly.
Does everybody follow me? Yeah.
When we find, is that Z in we found? Do we find Z in?
Well, that's going to be normalized Z. To get the actual value, you have to multiply it by what we normalized as Z. That's Z naught. Y'all hear me? So to get the actual input impedance, now we take this value. I hope y'all can see this. The 0.45 plus J 0.9, which is approximately right. Now you multiply that by Z naught, which was 50. So what is that going to give you? The actual value for the input impedance here, and I'll put this here, the actual value of Zn is going to be small zn, the normalized value times Z naught, or times 50. What is that? So it's 50 times 0.45. I wish you'd made it 100. It would have been easier. So it's 45 by 2. What is that? 22.5, right? So it's 22.5 plus what?
J45.
Plus J, and then it's going to be 45. Now, does he have that as the answer for that part?
Yes.
Okay, that's the input impedance. Y'all see how it's done? It really helps if you have a good straight edge, a good compass, and sharp pencils. And I should have brought mine. I will next time, and I'll do this. But I do this part on the board, and I get everybody working, because that way, if you're working this as I'm talking about, not just listening and watching YouTube or something, then it'll work. It works. You'll sink in. All right, what else does he ask in that one?
The distance from the load to the first voltage minimum.
All right, important, really important. Listen up. So I didn't cover this, but I'm going to answer questions as they appear. Now he wants to know where the voltage minimum is. You hear me? And while we're at it, we're going to get the voltage maximum. Now, listen to me on this one. The largest possible value for the voltage maximum will occur when you're moving along this arc and you come right here. That will be the maximum voltage. So anytime, wherever this circle is, remember that's constant reflection coefficient, but when the reflection coefficient is strict real and positive, which it's right there, now you'll get the maximum value of voltage. It will be 1 plus the reflection coefficient times V0 positive. The minimum value will occur on this trajectory when you come here. So that will be minimum V. And the reason is, and I'm not going to spend a lot of time on this, when you think about the equations for voltage, V of Z, that's V0 plus, right? Then it's times e to the j beta L, or minus j. Actually, it's minus j beta Z, plus the reflection coefficient times e to the plus j beta Z. Now, if you just listen to me on this, forget anything else. If you look at this, maximum value of that e to the j plus or minus j to b is 1, right? You all agree with that? Now, this reflection coefficient can be negative or positive depending on how far away you are from that load. And just trust me on this, as you move away from the load, that reflection coefficient is no longer the reflection coefficient of the load, but it's changing. Just leave it at that. But the minimum possible value, the maximum possible value is this is 1, and this is the magnitude, strict magnitude positive, which means it'll be V0 plus times 1 plus magnitude of gamma L. That's the largest value of voltage. That occurs when you're right here. Just trust me on this one, right? The minimum value will occur quarter wavelength away, and it will be when you're here. So he asked this question: how far away do you have to get to find the minimum voltage? All right, listen, hear me now. Minimum. We came in right here. The value was this, right? When we move from here to here, this distance from here to here will be the distance to the voltage minimum. Do you all hear me on this one? So what is it going to be? Well, that's 0.291, right? What is this? It's 0, right?
It's a 0.29.
So, I mean, but think about it. Normally, what I always tell people to do, and please do this, if you want the distance, find the point you're at here, which is 0, right? Isn't that wavelengths towards generator in the outer circle? It's 0, isn't it, class? Yes. Subtract this from 0.291. Right? You're going to get a value of minus 0.291. Do you agree with that? 0 minus 0.291. Then, because it's minus 0.291, you add 0.5 lambda. Now, this distance has to be less than a quarter wavelength, because if you move the quarter wavelength, we'd be up here, right? Y'all follow me? So it's got to be less than a quarter. So this actual distance that you're going to move for the voltage minimum will be 0 minus 0.291 plus 0.5. And what is that?
0.210.
Pardon me?
0.209.
0.209 lambda. You all agree with that? How many see that? Go ahead, say. If you had a question, ask it. If you don't understand, you can. I don't care. I mean, you can have all the fun you want in here. Laugh at me. Doesn't matter. I just need to know how I can help you, because that's what I'm here. All right, are you all with me on that one? That's how far do I have to go to get the maximum now? Think about what I just said. If I have to go that far to get the min, the maximum is a quarter wavelength away, right? So just add 0.25 lambda to that. You all hear me on that? And you get the maximum. You want to tell me where the maximum is? That's where I am. Just add 0.25 to that value of 0.209. 0.1?
0.459.
0.459?
Yeah, I think so, yeah.
All right, 459. Well, that's down here, isn't it?
So,
Wait a second. Wait a second. That's 0.25. 0.45 is down here, isn't it? Well, that's the distance. It's the actual distance you move. You move from here, and you'd have to move. I mean, if you move the 0.209, you're somewhere down here, right? That's the minimum. Then you would have to add a quarter wavelength, so you're off the length of the line, basically. There is no maximum on that line. You all with me? Yeah.
Does it always go clockwise?
That when you're at the load, you can only go one way, wavelengths towards the generator. So it is going to be clockwise. Now, if we're at the generator, and this comes a little later, then we go wavelengths towards load, which is the inner circle, if you look there. The outer is wavelengths towards generator. The inner is wavelengths towards load. You see that? Don't worry about that.
When he says in the question, the first voltage minimum, do you want like the second or the third?
Good question. He's saying, well, what if you want the second? Well, this line isn't long enough to have a second. It's a short line. Follow me? So actually, if you found a distance to the first, the second voltage minimum would be going all the way around and just add 0.5 lambda. Every time you go around the circle, it's a halfway. Does that make sense?
That makes sense.
That's the one thing you have to understand about this stuff. Now, doing problems is the way you're really going to learn. I want to do another problem. Is this making sense? I'm not going to get into impedance matching anything complicated now. I just want to go through the basics. So, if you look at the chapter, when you get good at these things, I mean, you can whip through problems so fast. It's not even funny. I mean, your calculator, you spend 5 minutes punching in numbers. You get this in about 10 seconds once you get used to it. All right, I want to do one. It's a little bit advanced, but we can do it. Do 2.29. And I'm going to erase this. I'll try to go a little slower on this one, but I want everybody, if you care, follow with me on what we're doing. This is something that has to do with, instead of starting at the load, we're going to start at the generator. And I'll show you what we're doing.
Drill 2.29?
No, at the back of the chapter, problems, 2.29.
Page 110.
Give me 1 second. What page of the problems on, class?
110.
Page 110.
Oh, that's smart.
All right. So for that problem, can you give that to me?
The input impedance for a 100 ohm lossless T line of length 1.162 lambda
1.162 lambda?
is measured as 12 plus J 42 ohms.
12 plus J 42 ohms. Who wants the load impedance?
Determine
Right?
the load impedance.
All right. This is a backwards problem. It's reverse engineering kind of. We had, before I said if you have ZL and you got a characteristic impedance Z naught and the line's length is L and wavelengths, you started here normalized. Then you moved, you identified where that point is in the Smith chart, and you moved and you went back to here and you found the normalized value of Zn, then you divided by Z naught, right? You all remember that? This is the reverse problem. So I'm going to draw my little Smith chart. And here's my equator. What's the characteristic impedance there?
100 ohms.
100? All right, so if you think about it,
What's the input impedance? That's what's in there.
what?
Input impedance. The 100 ohms is the input impedance.
Isn't Zn 12 plus J42?
I'm not sure.
Hold up. The input impedance for 100 ohm, that's Z naught. When it says for 100 ohm, it means the characteristic impedance is 100 ohm. So Z naught here is 100 ohms. This is the input impedance. Go ahead.
Oh, I was stretching. Sorry.
So now we're going to normalize it, all right? So go ahead and normalize this, and what do you get? Small Zn is going to be 12 by 100, that's a small value, plus J42 by 100. So that's 0.12 plus J.42, isn't it? So this is going to be 0.12 plus J0.42. Now, remember, I tried to show you the R=1 circle here. I need to find J.42. This is J.1, or J1 here, which is at the North Pole. This is about J0.42, if you can find that trajectory. Can you all see that?
Mm-hmm.
Class, can y'all guys see that? Now, this is a little tougher. This is a small number. 0.12 is going to be way out here. There's going to be a circle way where you're going to have to kind of extrapolate. It'll be like 0.1, 0.11, y'all follow me? Or 0.1, 0.2, something like that. Now find something that approximates R0.12. And this is your first point. So this is going to be the normalized Zn. Y'all follow me? Now, before, when we were at the load, when we moved, we went wavelengths towards generator, right? Now we're at the generator, you might say, and we're going to move in the other direction towards the load. Do you all follow me in that? So he says the length of this line is this. This is a great problem. What bothers you about it? Something should jump off the page and bother you, besides me. Anybody? It's greater than a half wavelength, right? Anytime you have a length greater than a half wavelength, you subtract half wavelengths from it until it's less than a half wavelength. Follow me? So subtract 1/2 wavelength from there, and you're going to see it's still greater, right? Subtract 2 and you get 0.162 lambda. So really, the line length I'm worried about is 0.162 lambda. Do you all follow me on that one? All right, that's the only thing I care about. Every time I go a half wavelength, everything repeats. Now, I started here, and I can do this a couple ways. I can use wavelengths towards generator and just rotate it in the other direction, right? Or I can go to the inner one and see wavelengths towards load. Do you all follow me now? Either one will do it. But first thing I need to know is what is this? If you go from the center of the circle, shoot it out here. What is the marker out here? Wavelengths towards generator. I'll do it both ways. I am out of time. What is it? Just give it to me.
0.64.
Is that what you got?
0.064.
Okay, hold on. Is that right? If you had a question, ask it. Go ahead. This is a good point. All right. Is it 0.064, did you say?
You said it's wavelengths towards load, correct?
No. Just give me the wavelengths towards generator first. I'm gonna do it both ways. I'm trying my best.
0.064.
Is that right? So it's 0.064 lambda. Now, hear me. We could go ahead and say we're at that point, but now we want to use this, and we want to go back this way, 0.162. If you think about this, if I went 0.42, that's here, right? Then I'd have to add 0.022 from here to here, right? Isn't that right, class? Y'all follow me on that? If I go from here to here, I went exactly 0.064, right? Now, if I keep moving, that's how far this distance is. If I wanted to add, since I'm at 0.162, oh boy, maybe I better not confuse you with this. Here's probably the easy, pardon me? I mean, if you just go ahead and subtract 0.064 from this, you get 0.0, what is that, 002? Is that right?
0.64.
Anyway, if you look at wavelengths towards load on the inner circle, what's the number? I am out of time.
0.436.
0.436? How many got that on the inner one? Can you see it? It's right below the wavelengths towards generator, outer circle. You get that? All right, now add this length to it. Add 0.162 to it. Tell me what you get. So it's 0.162 plus 436. So what do you get? 0.522 lambda, right? Isn't that right? So we have to subtract the half wavelength. Y'all follow me? What do you get? Now you have a value when I subtract the half wavelength from this. Now I got 0.022 lambda, right? Right? So if you look on wavelengths towards load, the inner circle, you're going to come down from here, and about here, you're going to see something that's going to have a value of 0.022 lambda. Or 0.22 on wavelengths towards load. Can you see that, class? It'd be on the inner circle. Can you see it now?
0.22?
Yeah. Now take your straight edge and just draw it through here. And I am out of time. But you're going to see a real and imaginary value there. Do you all follow me? You multiply that by Z0, that is the value of the load. Because this is the opposite problem we started with. Instead of starting at the load, we started at the generator and worked backwards. Y'all see me?
I don't like it.
Pardon me?
I get it, yeah.
All right, I'm going to give you a bunch of problems here. Please do them for next time. Now, next time is Friday. Friday is quiz day. So for the quiz, bring your own Smith charts. It's going to be simple stuff. Hint, it's going to be based on a homework problem. Hint, it will be identical to a homework problem with different values. Got it? All right. So do your homework. Can I say more? Oh.
Are you going to put 4 problems or 5 problems that you're going to post?
I'm going to post the homework tonight that I'm going to post.
Got it.
And I'll give you the videos that are excellent. And I'm sorry if these seem a little off. Okay, I'm really sorry. I didn't mean to.
I need to.